I would love nothing more than never to feel that way about it. Like, I'm so badly wrong. Too, I'm like, I can help. A morning walk today.
Still commute, you can live across the street, I'm just saying.
Yeah, you can. I'm saying I went for another walk.
All right, so last time. Some more d-Orbital splitting stuff. Talked about delta O and chemical reactivity and bond lengths. The strength of the splitting is dictated by the strength of the interaction between the ligand and the metal. And the ligand is the base and the metal is the acid most of the time. Except when there's pi back bonding, and then the metal is the base and the ligand is the acid. And that is a push-pull type of situation. The stronger the push and the stronger the pull, the greater the interaction and the larger the splitting. So this gives rise to some interesting situations, one of which is that Jan-Teller distortion we talked about, where if you have a degeneracy, the molecule says, well, one of these orbitals I can use to pull more tightly than the other one because it doesn't have the same number of electrons in it. In one case, you might have an electron at an anti-bonding level, and that pushes the ligands away. And if one of the two levels in what would be a degenerate situation is empty and the other is half filled, then the molecule distorts to enable stronger bonding with the empty orbital and a little weaker bonding with a partially filled one. That gives rise to these Jan-Teller distortions.
Does there need to be a vacancy or just a degenerate?
Well, there needs to be a difference in the occupation of the two, right? So, simplest way to say. So the changes that you get in the d-orbital splitting reflect that. And then we talked about an example where manganese hexacarbonyl gets reduced, the ligand pops off, you have an unpaired spin, two of these guys get together, you make a metal-metal bond, and that causes the splittings to evolve. Right? Pull the ligand off, the splitting gets smaller. So you can look at the geometry of a compound, excuse me, and deduce splitting. So let's do another example of that. Equal to hexacyanide. What is the charge on nickel 2 hexacyanide? How do we do this problem?
Oh, it's gonna be plus, no, it's gonna be minus one.
Okay, we have a vote for -4. How did you do that?
This HCN has one negative charge, so.
How did you know that?
Since we did that.
Good answer. Another way to think about this is
Lowest.
the simplest
Yeah.
neutral compound where you add hydrogens to fill it out is HCN, right? Like NH3 or OH2. HCN is the simplest compound, so pull off an H plus and you're left with a cyanide minus.
And we have plus
So you have 6 cyanide minuses, and this 2 means nickel 2 plus. The sum of those is 4 minus. So this is an octahedral compound. Cyanide is what kind of a ligand would you say? Pi acceptor. Actually not that great as a pi acceptor because of the fact that it's negatively charged. It's a pretty good donor. Cyanide's a pretty strong donor. It has pi symmetry orbitals. They are pi accepting, but really cyanide is a potent sigma donor. That's how I tend to think about it. It does both. Regardless, it's a strong field ligand. This is a strong field ligand. Strong sigma donation, some pi accepting, large splittings. So delta O is big. How many d electrons does nickel 2 have? Nickel, palladium, platinum is D10. So nickel 2 is 8 d electrons. Sigma star. Wrong. Pi bond. Why not pi star?
Because it's a pi acceptor.
Okay.
So it's going to lower the energy percentage of that pi orbital is going to be lower because that ligand sits lower energetically than the metal does. Therefore, the parentage of the pi bonding is going to lower, while the sigma raises. The parentage for the sigma is attached to the metal, and the parentage for the pi is attached to the light.
So that is the right set of principles, but what you said is not correct. Okay. So normally when you have a filled ligand like a phosphine or a chloride or a water, it's below the metal. But when you have a pi star orbital, that's an antibonding orbital on the ligand. And antibonding orbitals are high in energy. Those fall above the metal. So the pi star level of the cyanide is above the metal. When you make a bond between the pi star and the metal, the d electrons on the metal drop in energy. So because the metal is the parentage for these electrons, these are like the d orbital electrons on the nickel. They start below the pi star level of the. So they drop, and that makes them the bonding. This is the bonding orbital. Okay. So this thing is hypothetical. 4 minus, yeah, you should be skeptical. 4 minus is a lot of minus. This compound, if it existed, would spontaneously use cyanide. You've got unpaired electrons in the sigma star. There's not a lot holding the ligands on. 4 minus thing, it's just going to pop off a negative charge. And you're going to end up with nickel 2 pentacyanide. So I pulled off this lone pair with a negative charge. That does not change the valence on the metal. You get pentacyanide, trianion. And in fact, this can happen again. This one's reversible. This compound here is C4B. This compound here is D. Now, what does the d orbital splitting diagram for that look like? What does it mean that it's C4B? Is there a geometry name that you might give it? Square planar. Sorry, square pyramidal is what I would say. Yes. This compound, square planar. Okay. So this is a square planar compound. You bring in an axial cyanide, it just sticks up, kind of like the manganese example we did last time. So the principal axis here is a C4 axis. It's along that vertical cyanide. And what is that going to do to these splittings? Now these two here, x squared minus y squared and z squared. These are the sigma orbitals, right? These are the d orbitals pointing at the ligands, and these are the d orbitals pointing between the ligands. I'm gonna say that again, because this is something that you guys really gotta have on lock. You're gonna have to do this. You've heard me say it, so you're like, yeah, but you need to know this. Z squared and X squared minus Y squared point the ligands. XZ, YZ, and XY point in between the ligands, right? So now we've taken off a cyanide, made a pentacyanide, and that's along the Z axis. So what's it gonna do? Go ahead, what's it gonna do? Well, I'm just gonna pull it off completely. So yeah, it's elongating to the point of being gone. What's that gonna do to these levels? Who's affected by that?
All Z axis based.
Anything along Z is likely to be affected. So is X squared minus Y squared affected?
It's gotta match in order to equalize out the energies of the orbital splitting.
I can't hear what you're saying.
It's gotta match in order to equalize out the energies of the orbital splitting, so it's gonna, whenever the Z squared stabilizes, this X squared minus Y squared is gonna have to destabilize in order to make a split, a tiny amount.
No. In the Unteller situation, it's slightly different. So in this particular example, we're just pulling something off of what is bonded to Z squared. The other four, which are going to be in the final square planar compound, are bonded to X squared minus Y squared. X squared minus Y squared doesn't care, essentially, that you lost the ligand along Z. These things can't really fully be treated in isolation, but we're going to treat them in isolation because I want you to recognize that Z squared is the d orbital that's affected here. That's the one that lost its ligand.
Wait, but how do we know that? Because aren't they the same in like energy?
Not in the product.
Oh, that makes sense.
So what's going to happen to Z squared? Is it going to go up or down? It's going to go down.
I think it goes down, because you're removing an electron, right? So the energy will go down. If you're pairing it with the electron that's attached to your cyanide, then it's going to be a higher energy. That's how I think of it.
Okay. I think that's a very rational thing that you said. How many people think Z squared is going to go down?
I don't know.
Not clear. What kind of an orbital is this? So when you pull a ligand off of it, is it now more or less antibonding?
More. It's less.
If I have two orbitals interacting with each other, okay, let's just do hydrogen 1s. You push them together, what happens? You get a bonding and an antibonding. The more they overlap, the larger the spacing, right? You pull them apart, and they go back to being hydrogen atoms in the ether, right? No interactions anymore. So if this is an antibonding level, what happens when you pull everything apart? It goes back to where it started from, which is where the metal atoms level was, right? So is that up or down?
It's up because it's a pi acceptor, right? The like, so.
Well, we're not talking about pi yet. We're just talking about sigma. How many people think it goes down? That's surprising. It goes down. You pull two things apart, and there's no longer a bond. And so anti-bonding comes back to non-bonding. All right, so Z squared is going to go down. And X squared minus Y squared is going to stay put. And they're both still sigma star. Why are they both still sigma star? We just pull the ligand off of our Z squared.
Z squared still has a ligand on the other side.
Yeah, it's got one on the other side of the complex, and it's got the donut. Everybody's taking a bite of the donut in the square plane, right?
Wait. I'm not
Something to keep you guys.
I'm not entirely sure why it would still be sigma star. We said it would drop back to the metals level.
Well, only if you completely pull everything to bits, you know. But we're not pulling everything to bits. We've got 5 cyanide ligands. Some of those ligands are still interacting with that Z squared orbital.
Oh.
Stop. Go ahead, Tori.
So at this point, are we not really concerned with like labeling them T2G or EG because like? with
We
this-
are.
Okay,
But for right now, I just want to think about how the ligand field splits the Ds, okay? And we'll do the symmetry labels later. And generally speaking, the symmetry labels, I don't get too worried about. Have to learn it, you know, I'm gonna ask it, but what I really want to know is what the order of the orbitals is. Because I want to know where the electrons are. So both of these guys are Z squared. How many ligands are bonded to X squared minus Y squared? How many ligands are bonded to Z squared? 5.
Here's one. The d-orbital contains the form going.
That's right.
Oh.
We have 5 ligands total. Right?
Yeah.
But you're saying that,
Oh.
how many of them, you're saying that there are 2 on the X squared and the Y squared? Or
4.
There's 4, okay. But then there's also 5 on the Z squared.
Yep.
Okay, so they're just alternating, like, how does that work? I mean, that's more than.
You should draw them out.
Yeah, like when you imagine the orbital, you can see how the.
If you can't see this immediately, I suggest you draw them out. Okay? This is something you have to be able to just. Right. So what about these ones here?
X, Z, Y, Z raise, X, Y stays.
X, Z, Y, Z go up. Why do they go up?
They're bonding orbitals, so as we pull back the pi star, the pi antibonding from the CN orbital gets further away, this binding interaction weakens.
Yeah, so you're weakening the bonding interaction by pulling off a vertical ligand along Z. And in this case, this is a bonding level. These electrons in this compound are stabilized by the CN pi stars. You just pulled one off, they're not as stabilized anymore. Which ones are not as stabilized? Well, the ones that are interacting along Z. So this one doesn't care. Not involved in any kind of pi interaction with the Z, the cyanides along Z. It's only involved in pi interactions with the cyanides in the plane with the 4 cyanides here, or in the square plane of this compound. So these XZ and YZ orbitals, they just lost some of their stabilization. Those pi star, pi acid orbitals just went away. Those are going to go up. XY stays the same. They are both still pi bonding. In fact, the XZ-YZ make connections with the 4 in the square plane. They also make connections with the 1 axis. Okay. So now, how many d electrons do we have for nickel 2? 8 d electrons. You might say, well, wait a minute, why don't we put it up here? Aren't they unpaired right here? What happened? You need to know the energy difference between these two, right? In order to tell whether or not that one's going to go up here. You got to pay a ionization energy penalty to move it to that level to get some of the exchange. Reduce the Coulomb interaction. What's the difference between those two levels? We don't know that. Yes. With strong field ligands, I pick low spin. All right, let's do this again. Pull off another cyanide. What is this one going to look like? More of the same. Just pulling another one off of the Z direction. Okay. X squared minus Y squared is unaffected. Z squared is coming down. XZ and YZ are coming up. And XY is staying the same. In D4H, the X and Y directions are indistinguishable. The X and PY are indistinguishable. So are XC and YC. So they are an E set. Parentheses around them for that. Now, what are the parent, or what types of interactions do we have here? Sigma star, sigma, non-bonding, pi star. Sigma star, definitely sigma anti-bonding. 4 ligands, all interacting with this orbital. Very anti-bonding. Z squared, non-bonding. Don't forget about the donut. This is sigma star. XZ, YZ. We just pulled out both Z. Both ligands along Z. Are these bonding, non-bonding, anti-bonding? Why are they bonding?
The X and the Y, which is
Because the ligands, the cyanides have 2 pi symmetry orbitals. Some of those p orbitals are vertically oriented and they can make bonds to those XC and YC ligands. This is pi, this is still pi.
I have a question. Are there cases when it's not like conserved? And by conserved, I mean like throughout, it seems like the degeneracy doesn't change, nor does like what the orbital, I guess, stands for or does. Is that like a rule or is that?
It's nice to do it that way. You could pick your z-axis pointing at some weird angle and then, you know, derive new labels for the d orbitals that would be unrecognizable to you and redo all this stuff and it would be gobbledygook. We point the z-axis in a way that makes sense. We choose it as the principal axis in our compound.
Yeah,
So z is sort of consistently oriented in these 3 compounds.
I don't know if my question was clear enough, but I meant more like through each step of the process, the degeneracy of everything is conserved, right? Like none of, like none
No,
of the.
because these are triply degenerate.
Ah,
Here they're the same. That's just a consequence of the symmetry of the compound. So
that makes sense.
these compounds here, they have right angles. That makes them really nice and easy to do. Right? Z squared and X squared minus Y squared point at the ligands with 90-degree angles. XZ, YZ, and XY are in between those ligands at 90-degree angles. You get that type of a situation when you have strong sigma bonding. Compounds like these could be tetrahedral. Why isn't this tetrahedral? There's a tetrahedral form of this one. It likes the square planar one. Square planar one supports better sigma bonding. We'll see why. Same here. This thing is square pyramidal. It could also be trigonal bipyramidal. But it's not. That's a consequence of the ligand type. Okay, now, what if it's not that way? This is your last group theory problem, or novel one. And it's kind of the hardest. Turns out it's actually the easiest, I think, because it's sort of mindless, as you'll see. Let's do D3H instead of C4B. Okay? Instead of nickel cyanide, we're going to do iron pentacarbonyl. Iron pentacarbonyl is D3H. So before I get into this, I want to say something that I think you're going to hear me say it a couple of times today, and it's really going to save you. a lot of heartache, okay? So it's good to remember this. Whenever you have an odd principal axis, like C3 or C5 or C7 or C9, if you have an odd principal axis, X and Y are indistinguishable. And they transform together as an E set. So I'm going to say it again. Whenever you have an odd principal axis, X and Y are indistinguishable. And you're going to be sitting there drawing calcs and trying to do the group theory and stuff. You're going to be like, well, wait a minute. If I point the X over here, and then what is the Y doing with those things? Don't try and do it. This is what I mean by it's mindless, okay? X and Y are indistinguishable in a complex with an odd symmetry axis, the principal axis. That makes XZ and YZ indistinguishable. It also happens to be the case that X squared minus Y squared and XY are indistinguishable. Okay? So this is all you need to know to solve this problem. That's it. You know how to do the group theory work. It's going to look a little bit funky. It's not hard if you just remember that. Some metal complex with 5 permanent units around this, the equatorial plane and 2 vertical ones, same as this one. You have an odd principal axis, X and Y are indistinguishable, XZ and YZ are indistinguishable, and X squared minus Y squared and XY are indistinguishable. Okay? Remember that, your life's going to be easy. All right, so let's do the group theory on 5 ligand sigma. We have 5 orbitals around the metal. Do nothing gives 5. 2 of them are along the C3 axis. 1 of them is along a C2 here. Sigma H has 3. These guys. All right, gamma XYZ. How do we figure out what gamma XYZ is? Look at the character table is the answer. Okay. Now, how do we do gamma total? Gamma total is the sum of sigma and pi. Here's sigma. How do we get the pi? XYZ times 5 ligand sigma gives you gamma total. 15, 0, minus 1, 3, 0, 3. 10 ligand pi. We've already done the sigma. We have 2 pi orbitals per CO. There are 5 COs. We get 10 ligand pi here. We get that by subtracting 5 ligand sigma from gamma total. 10 minus 2 minus 2, 0, 0, and 0. All right. So here's what 5 ligand sigma looks like. And 10 ligand pi. A lot of A's and E's and primes in there. Primes and double primes. And let's do the metal 5 ligand sigma. And 5 ligand sigma plus 10 ligand. We're gonna do sigma only picture, and then we're going to do sigma and pi. So we have our five d-orbitals here. We've got an A1, we've got an E prime, and we've got an E double prime. Which are these? I just told you the answer 90 seconds ago.
It's like the S and T orbital.
X, Y.
Which one is the A? A1.
Z squared.
We're talking d orbitals now.
Z squared.
Z squared. Okay. Z squared is often A1. E prime and E double prime. Well, the primes are sort of hard, right? Let's not worry about which one is prime and which one is double prime, but XZ and YZ, those two guys go together. They're above and below those three COs which fall in a plane. X squared minus Y squared and XY point at the three COs in the plane. You can see how those two are similar. Right? Those two make sigma bonds with three COs. They form an E set. That's all you need to know to do this problem. X squared minus Y squared and XY form an E set with these three COs around it. Right? No right angles here. Hard to do this by inspection. Just going to tell you the answer. You remember, okay?
Wouldn't the character table tell us, or?
Sure does, yeah. You need to know this stuff because you're going to do these problems without a character table. You need to be able to do these orbital splittings in your head, like we just did for the nickel problem. You need to know that X and Y go together. And that means X squared minus Y squared and XY go together. And that means XZ and YZ go together. Okay? All right, so let's get some ligand sigma orbitals on the board here. We have 5 of them. 1, 2, 3, 4, 5. How many of the ligand sigma orbitals have the same symmetry as the metal?
Wait, what?
How many of the ligand sigma orbitals have the same symmetry as the metal? We're just talking d orbitals. Okay. A different way to ask this question is, which orbitals on the metal make sigma bonds? Z squared.
X squared minus Y squared will as well.
X squared minus Y squared and XY are the ones in the plane. XZ and YZ are above and below that plane. So who? Z squared and what makes the other sigma bonds in this compound? XY and X squared minus Y squared do. They're in the plane of the three COs. Okay? So you have two A1 primes, an A2 double prime, and E prime. Is that prime supposed to be there? It's not in any of these other ones. I don't think there is an A1 prime, so I'm just going to say A1. I have to go look at my textbook. I think it's just A1. All right, so there's an A1, right? That guy's going to interact with the Z squared. And we've got an E prime. So what does that mean E prime is? The one that overlaps the metal, and that's X squared minus Y squared. So that means E double prime is the one that doesn't make sigma bonds. That's X, E, and Y. All right, so we've got two A1s.
What about
E prime
XY?
and A2 double prime. XY is going to be part of this E prime set. Okay? So I'm going to just say bonding orbitals You get a bunch of bonding orbitals, I don't care about. What I care about is the d orbital splitting. Let's do the d orbital splitting. Now, sigma only picture. Which sigma bond is the most important? Or which sigma bonds or which orbital overlaps are the most significant? You got three to pick from, two of them are the same, they're degenerate, right? So what's more significant, the z squared interaction or the x squared minus y squared? You got a z squared over there. Anybody else like z squared? Z squared's pretty good. I mean, you've got two ligands along the z-axis pointing right at it, and you've got three ligands all taking a bite of the donut. X squared minus y squared, you got two d orbitals split only between three CO ligands. Right? So that's z direction. That's where the action really is happening. And that's going to make these d orbitals here split like this. Z squared is going to be the highest. So some of these things here are going to go like that. So we're going to have an A1 orbital up here. We're going to have an E prime up here, and we're going to have an E double prime down there. This is the Z squared. This is x squared minus y squared and xy. These guys down here are non-bonding orbitals. Okay. So to do this splitting diagram, you have to estimate the relative importance of sigma bonding. And the way you do that is by asking, do the ligands point at the orbital directly? When you have a compound with right angles, straightforward. When you do not have a compound with right angles like this one, the cases where the d orbital points directly at the ligands, more significant than the cases where the orbitals don't. So 90-degree angles, great for sigma bonding. Angles that are not 90, sigma bonding is not as good. Okay? Now, let's add some pi to this. Do this again. Ligand-based orbitals down here. 1, 2, 3, 4, 5. 2A1, E prime, A2 double prime. We're going to need some bond orbitals. And we've got this d orbital splitting here. We already know what the sigma effects are. So let's add some pi. So we're going to throw in our pi orbitals up here. Why are they up there? Because there's anti-bonding levels on the COs. Okay? That's why they're higher than the metals. So let's get our 10 orbitals up here. A2 prime, A2 double prime, 2E prime, and 2E double prime. Right there. Which of these d orbitals are of pi symmetry?
All the ones with X or Y.
Almost everybody except for that A1. Both E prime and double prime are of pi symmetry. So what is that going to do? We're just adding pi acids here, right? These are pi acid orbitals. They are acceptors. If you have electrons in this metal complex, those electrons are going to be stabilized by pi acids, right? So they're going to go down. So these two levels are both going to drop. This one is unchanged. This is not pi symmetry. These are pi symmetry. These will both be stabilized by these orbitals here. Yeah.
Okay, so I just want to clarify because I think I got the same thing wrong earlier today when I tried to answer the question. This is a CO that we're looking at.
Yep.
Okay, so it's a pi chip.
Right.
So it's the conduit, and can do pi back bonding. So it's going, when we put it in the MO diagram, it's still above the metal.
That's
Pi is always above the metal. It's always.
unless it's a pi donor.
Pi donor is below. Okay. That's what you said.
To stabilize the d electrons of the iron. So we're going to see some d double prime going down. We're going to see this. Both E double prime and E prime drop relative to the sigma. So now we have a sigma star up here. How would you label this one? It's pi bonding. That's right. What else? Also sigma antibonding. Right? Sigma antibonding.
Oh, it can be both, right?
You got it. That's sigma star and pi. Cool. What about this one? No sigma? What orbitals are these?
X, Y, Z.
X, C, Y, Z, and where are those in that compound?
The delta in between the Y lines. Or going towards the center.
Are these in between the ligands? Yeah, kind of, sort of. There's some overlap though. These are above and below the plane of the three COs. There's no sigma interaction. That's just fine. X, Z, Y, Z. X squared minus Y squared and X, Y. And Z squared. Okay. How many electrons? And ruthenium and osmium have 8. These are filled. Think about this molecule for a second. The HOMO is a sigma star orbital. Seems bad. Why do those COs even stick on there? The electrons doubly occupying the sigma star level. That's weird, right? We talked about putting one electron in the sigma star and the ligands want to pop off. Now you got 2. But it's also d pi. Right? So those ligands in the equatorial plane, which are overlapping with these d orbitals here, they hold on for dear life using their pi star level. Now, there's also an s orbital on the iron that's empty, and there are 3 p orbitals on the iron. The orbital character is going to be sigma star level is filled. Weird. That's kind of cool. I think if you can visualize that, you understand this stuff pretty well.
Are you saying that because there's a superfluous amount of, there's a lot of electrons that are sitting in that orbital metal that the CO, you're asking, well, why would the CO attach to this metal if you have all these electrons? There's multiple force, right?
In the sigma star orbital, sigma bonding is most strong.
So is it the pi back bonding that allows it, right? Because you're able to like use it as a conduit to push the electrons onto the oxygen.
Correct.
It's like we're doing both sides separately, and then when we combine them, we get like this clear picture.
You got it. There you go. All right, now, one more point about that, go ahead.
Does that mean that this has the distortion where the Basel model?
Yes. Good thought. Now, one more thing about this, I already said this, I think, but I just want to hammer it home. D3H, this geometry, this is a good pi bonding geometry. You have 4 orbitals of pi symmetry. C4b is a good sigma bonding geometry. This kind of a compound likes this D3H structure because it has pi acid ligands. The cyanide one, and because the metal is electropositive. Right? These pi interactions are a back bonding interaction. The metal is giving up electrons to the ligand. Iron 0 is electropositive. Iron rusts in air. It's electropositive. So when you have CO, electron withdrawing ligands, and an electropositive metal, you're going to see pi bonding geometries. Pi bonding geometries tend not to have right angles. If there's a choice between a right angle geometry and non-right angle geometry, that situation will choose D3H. Nickel cyanide is different. Cyanide's not as good of an acceptor. It's mostly its own. And nickel is not as electropositive. Same is true of square planar and tetrahedral. Tetrahedral is pretty good pi bonding geometry, not nearly as good for sigma bonding. All right, so let's write these things. Let's draw some cells here. Let's draw our A1 now. Easy square. There's an A1 cell. That's the orbital plane along the z-axis. And the 2 lobes above and below the plane there point right at the ligands, and so is the donut. So that's a nice sigma bonding orbital. Now, let's do the other ones. We're going to forget about the z for a second and just flip this thing over and look down the xy plane. So this is E prime. There's our 3 COs around the iron. To draw these cells, pick one of the COs and call it X or Y. Okay? Makes your life easy. Pick one CO and call it X or Y. So let's draw the d orbital that points directly at this ligand. Okay. There's a d orbital drawn on top of the ligands. Where one of the lobes points directly at one of the COs. Just commit to that, and then everything gets easy after that. So we're going to have one orbital over here, and you know how to shape that one, right? The lobe of the d orbital is pointing right at it is going to have the same shape as that guy. And what do we do with these other 2? What angle is this? 120, right? Where are the nodes in a d orbital? 90 degrees, 2 planes, right? 90. So this nodal plane to that nodal plane has a more acute angle than the 120 degrees between those ligands.
Wait.
So if I color these things in, what color should they be? Not shaded. They're 120 degrees. The angle between nodal planes is 90. They're outside of those.
Oh,
Okay, so they're on this side. Let's do the other one. How do we do the other one? How do we draw a d-orbital on that ligand from there?
You have the on the plane directly towards the iron. You have those lobes for the to be not shaded anymore. You change the shade. And then the two that you have outside the plane are going to be shaded this time.
Well, let's call this one here x squared minus y squared, okay? That's my preferred orbital for pointing right at the ligands between the two, xy and x squared minus y squared. So we're going to call this one x squared minus y squared. And where is xy relative to x squared minus y squared?
Where x squared minus y squared's nodes are, so just
Rotate it by 45 degrees, because those two d orbitals need to be orthogonal to each other. So the lobes of xy sit on the nodes of x squared minus y squared. You just take your d orbital, rotate it 45 degrees, and you have the other one. So now, instead of nodal planes like that, I'm going to have nodal planes vertically and horizontally. There's a nodal plane. There's a nodal plane. Let's just color it in. "45 degrees, right? So how do we do these? This one's pretty easy. It's sitting on a nodal plane. And it turns out that way if you pick this one to point directly at that ligand. Okay, so that's why you do that. So this guy's got nothing. No shading. Doesn't have any component because it sits on a nodal plane. How about these? Pretty easy. No nodes even close. Okay. They're going to be closer to this nodal plane than they are to that one, but they basically make nice single bonds with those two nodes. Right?
yeah, and that. I have a question. So we have x squared and y squared. We have like two orbitals for them in our diagram. So from that, can we do we get any information from the diagram that we drew when it comes to drawing these drawings, or is it all just like geometry and visualization?
It's just visualizing. This is a way to represent that same wave function. So orbital interaction or orbital drawing. All right, now let's do. Remember that E prime is not just a sigma symmetry interaction; it also does pi. So let's do the products here. Okay. This time, E prime pi. This guy over here is the sigma. Okay. And I'm going to pick the same orbital I did before on the left. Let's draw some high star orbitals on the CO ligands. I'm just going to draw the p orbital symmetry over here. Is there a p orbital on this center here that overlaps with this guy? There's not, okay, because there's a node running through any p orbital that's oriented for pi bonding. Doesn't overlap with that guy, so that gets nothing. But out here, pi bonds. Let's do the other one. Their same d orbital, we just rotated by 45 degrees. Now you can see how a p orbital here makes a really nice pi bond. That d orbital arrangement shares the nodal plane exactly of that p orbital. And how about these ones here? Any kind of overlap?
No.
They're further to one side of the other.
They're further to one side than the other.
They're not exactly in the middle.
Well, where are the nodal planes and where are the ligands? The angle between the ligands is 120 and the angle between the nodal planes is 90. So they're not perfect. Here, perfect orientational arrangement where this lobe and this ligand fall exactly along the same line. Here, that's not true anymore. Right? The maximum for this d orbital and this d orbital are 9 degrees apart. These ligands are 120 degrees apart, so they're wider. So which of these two lobes is shaded, top or bottom? Top. This one? Nope. Did I get it wrong?
So we basically need to think about the angles, right?
You sure do. You got it.
So the nodal plane, I'm sorry, nodal plane on the right hand, so we cut down the middle, cut across like that. That means that the nodal plane is shared with that one p orbital. Those p orbitals are not sharing the nodal plane.
These two?
Yes, those two.
The issue is it this lobe or this lobe that overlaps? That's the question. It's this lobe that has a positive interaction. Because this p orbital is, despite my drawing, it's sort of on this side of the maximum of that lobe. So that side of the p orbital has symmetry.
That'll be a smaller pie chart, right, compared to the.
Yeah, well, there you go. So maybe I should have drawn these more smaller, basically. This one, that looks really good,
Yeah.
right? This doesn't look as hot. So probably down here, we should have drawn a smaller orbital than I did. Okay. All right. Let's do this one more time. Who are we forgetting? Which one haven't we done so far? Well, yeah, but which d orbitals? Nobody knows what d double prime. XEYZ. Where are those? Above and below the trigonal plane. Okay, the outer plane and my trigonal. I'm gonna pick one. This. I've chosen this guy to be in the plane of the board. I've chosen the plane of the board to be XZ or YZ, doesn't matter. Same sort of maneuver that I did over there. Right, this guy is in the plane of the board is going to be the XZ plane. Okay, so now, is there any signal overlap here? Why not? Well, that's true, but tell me.
On the node.
Yeah, there's two nodes here. And those two nodes fall right on the ligands, so there's no sigma interactions here. Okay? So what kind of orbitals are we drawing then? Pi. So put some p orbitals on here, make them overlap. That's all there is to it. Here's one. That one's pretty good. How about over here? I like that. That's pretty good. Down there, that's pretty good. How about this one? Just draw all the orbitals that form a pi bond. Picking Z and picking X and Y in a sensible way. Okay? This is Z. This is X. Any Y? Where's the Y? Y is like this, right? Is there any pi symmetry Y component to this guy? I don't see any. This is an XZ orbital. There's no Y. XZ has no Y. Michelle Silverstein told my kids last night. XZ has no XZ has no Y. Where's the Y? If you put a p orbital here, it's in the nodal plane of this XZ orbital, and it better be. Okay, so there's no Y.
Wait, are you asking if the YZ orbital has model interactions?
No, that's different. Yeah, sorry. Maybe my question wasn't clear. Let's do the XZ. Sorry, the YZ. Yeesh. This guy some color here. How do we draw pi symmetry p orbitals on the ligands? This guy have one? How about this one? Yeah, looks kind of similar, doesn't it? How about these two?
Oh, they should have, because they're different. The one on the plane of the board doesn't have.
Yeah, there's some pi symmetry back here.
The one on the plane of the board doesn't have.
The doubtful look.
Okay. All right, So X, Z, and YZ interact with pi orbitals above and below, which is kind of cool, sort of in the plane and out of the plane. Although it's getting a piece of X, Z, and YZ. X squared minus Y squared and XY really only interact with the limits that are in the plane. Look at all those pi bonds. A lot of pi bonds here. B3H is a good pi bond in geometry. So, how do you solve this problem? X and Y go together with a non-principal axis. That means X squared minus Y squared and XY transform together, and that means XZ and YZ transform together. You can remember that. This is really easy. The rest is just plug and chug.
Wait, how do I write it? What is it exactly that you said? I've been trying to write it down, but it's like so many different letters that I'm not.
When you have an odd principal axis of rotation, so something like D3H, D5H, D9V, whatever you want, odd principal axis of rotation, X and Y are indistinguishable. They become an E set. They transform together. And so do X squared minus Y squared and XY. And then separately XZ and YZ. Okay? You remember that? This is easy. Okay, so you're going to be doing these odd principal axis d-orbital spring diagrams. You're going to be wrapping your brain. You just got to remember that. Odd is actually kind of easy. That's sort of like give you a headache for a minute, and then you're going to remember that rule.
Is this the first time we've had an option for axis?
Yeah. All right, so iron and carbonyl. This is D3H, D8. It's not C4B. 4 out of 5 d orbitals for 5. Okay. Iron is electropositive. And you've got good pi acceptors. Okay. So iron pentacarbonyl likes this geometry. Now, let's take a look at this one here. Very distinguished chloroplatinate. How many d electrons for tetrachloroplatinate? 2 minus complex, because 2 of those chlorides count for 2 of the negative charges, and that leaves you with platinum dichloride left over. So this is platinum 2. How many d electrons for platinum 2? Nickel platinum platinum starts with 10. That's the end of the D series. Nickel platinum platinum is the end of the D series. So nickel 2 is D8, just like iron pentacarbonyl. So this guy, D4H, D8, it's not D. Okay. You have 3 out of 5 orbitals of pi symmetry. Which ones?
X, Y, Z.
XY, XZ, and YZ. Just like an octahedral, it's the d orbitals that point in between the ligands. When you have 90 degrees, it's easy. Z squared and X squared minus Y squared are sigma. And XY, XZ, and YZ are bound, just like an octahedral. 90 degrees is easy, they separate like that. Very deeply. So XY, XZ, and YZ all apply symmetry here. 3 out of 5 instead of 4 out of 5. You got strong sigma bonding here. Platinum 2, electropositive, electronegative. It's really pretty electronegative metal. That's why they make rings out of it. Doesn't oxidize. Platinum likes to be platinum 0, which is makes it a pain in the butt to do chemistry with. Likes to precipitate as metal. This is an electronegative metal center. So I'm going to tell you this right now. You're going to see this like 30 times the rest of the class. D8 complexes on the right-hand side of the periodic table over by nickel, palladium, platinum. They're square planar. You go toward the left and you start getting these odd angles. Because metals become more electropositive and less good at sigma bonding. And you start getting tetrahedral or E3H instead of C4B or whatever. All right, rhodium 1, also D8. It has intermediate properties. It does both, kind of depending upon what the ligands are. And in fact, when you have those metals, they flip around between the various geometries because the geometries are closer in energy, so they just sample them rapidly. This is especially true for 5-coordinate geometries. Okay? Between the D3 and C4B, or probably I should have written trigonal bipyramidal and square pyramidal forms. All right, that's a good place to stop. And that we're going to keep doing d-orbital splittings. But that's basically the last time we're going to spend talking about group theory in this class. You have to know that, obviously. And now we're going to sort of put down the group theory a little bit, and we're just going to start looking at d-orbitals and estimating bonding interactions. What you looking for, Abdullah? Rapidly interconvert. 5-coordinate structures rapidly interconvert. So, what do you need to do? What do you need to know to do iron pentacarbonyls? D-orbital splitting in MO diagram. X and Y go together. You have a non-principal axis, X and Y are indistinguishable. It's going to bother you. You're going to be trying to draw these souths and like, oh, wait a second, what do I do? Just remember X and Y go together. Commit, when you're drawing a south, put one of the ligands as the X direction. Okay? All right. We will see you next week. Have a good week.
I also had a question about the 9 creeps. So you said something about downward orbital